Welcome to Chapter 3, Aircraft Construction. In this chapter, we'll take a comprehensive look at how aircraft are built, certified, and designed to fly safely and efficiently. We'll explore the regulatory definitions established under Title 14 of the Code of Federal Regulations, which form the foundation for how aircraft are categorized and certified. From there, we'll move into the core aerodynamic principles that shape structural design decisions, followed by a detailed examination of the major components that make up a typical aircraft. We'll also cover the various construction methods used in aviation, from traditional aluminum airframes to modern composite materials. Finally, we'll introduce glass cockpit technology and the advanced instrumentation systems that are increasingly common in today's aircraft. Whether you're working toward a private certificate or building your foundational knowledge as an aviation professional, understanding aircraft construction is essential to operating any aircraft safely and confidently. Let's get started. The Federal Aviation Administration defines an aircraft as any device used or intended to be used for flight, as outlined in 14 CFR Part 1. Within that broad definition, an airplane is more specifically an engine-driven, fixed-wing aircraft that is supported by the dynamic reaction of air against its wings. That distinction matters because not everything that flies is an airplane. The FAA recognizes several certification categories of aircraft, including airplanes, rotorcraft, gliders, lighter-than-air craft, powered lift and powered parachute aircraft, and weight shift control aircraft. Each category has its own set of regulations and certification requirements. You'll also hear the term advanced avionics aircraft used in modern training environments. This refers to aircraft equipped with a GPS moving map display and an autopilot system. It's important to note that while this term is widely used in aviation training, it has not yet been formally codified in 14 CFR Part 1. As you progress through this course, understanding these definitions and categories will give you a solid regulatory foundation for everything that follows. The FAA certifies 3 specific aviation products: aircraft, aircraft engines, and propellers. Each of these products must demonstrate compliance with airworthiness standards found in Title 14 of the Code of Federal Regulations, commonly referred to as 14 CFR. The applicable standards depend on the category of product. Part 23 covers normal, utility, acrobatic, and commuter category airplanes. Part 25 applies to transport category airplanes, which are held to more rigorous standards given their size and operational complexity. Parts 33 and 35 address aircraft engines and propellers respectively. When a manufacturer demonstrates that their product meets all applicable requirements, the FAA issues a type certificate, along with a type certificate data sheet, commonly abbreviated as TCDS. The type certificate data sheet is a critically important document. It captures the approved specifications, limitations, and configuration details for that specific product. Both the type certificate and the TCDS are publicly available through the FAA website at faa.gov. As an aviation professional, knowing how to locate and interpret these documents is an essential skill you will use throughout your career. There are 2 types of airworthiness certificates a pilot needs to be familiar with. The first is the standard certificate, which is white, and is issued for normal, utility, acrobatic, commuter, and transport category aircraft, as well as manned free balloons and special class aircraft. A standard airworthiness certificate remains valid indefinitely, as long as the aircraft receives its required maintenance and inspections on schedule. The second type is the special airworthiness certificate, which is pink, and covers a broader range of aircraft categories including primary, restricted, limited, and light sport aircraft. Special certificates also apply to provisional certificates, special flight permits, sometimes called ferry permits, and experimental aircraft. Regardless of which type applies to the aircraft you're flying, the airworthiness certificate must be aboard during all flight operations. It's one of the required documents you'll need to verify during your pre-flight checks. One important distinction worth noting involves light sport aircraft. These aircraft are designed and built to consensus industry standards rather than traditional FAA airworthiness standards. A single type certificate covers the entire aircraft: the airframe, engine, and propeller are all certified together as one unit, which differs from how most other aircraft categories are certificated. Keep this in mind when working with LSA documentation. Every aircraft in flight is subject to 4 fundamental forces, and understanding how they interact is essential to understanding flight itself. These forces are thrust, drag, lift, and weight. Thrust is the forward force generated by the power plant and propeller. It acts parallel to the aircraft's longitudinal axis and works directly against drag. Drag is the rearward retarding force that opposes thrust. It is caused by the disruption of airflow around the wing, fuselage, and any protruding objects on the aircraft, and it acts parallel to the relative wind. Lift is generated by the dynamic action of air moving over the wing. It acts perpendicular to the flight path through the wing's center of lift, and it directly opposes weight. Weight is the combined load of the aircraft, crew, fuel, and cargo. It acts vertically downward through the center of gravity and opposes lift. In straight and level, unaccelerated flight, these 4 forces exist in a state of equilibrium. Thrust equals drag, and lift equals weight. Any disruption to that balance will cause the aircraft to accelerate, decelerate, climb, or descend. Mastering this concept is the foundation for everything that follows in your study of aerodynamics. Every aircraft rotates around 3 axes, and all 3 pass through a single critical point known as the center of gravity. Understanding this relationship is fundamental to safe flight operations. The longitudinal axis runs from the nose to the tail through the center of gravity, and rotation around this axis is called roll, controlled primarily by the ailerons. The lateral axis runs from wingtip to wingtip through the center of gravity, and rotation around this axis is called pitch, controlled by the elevator. The vertical axis runs straight up and down through the center of gravity, and rotation around this axis is called yaw, controlled by the rudder. Now, the center of gravity itself is the point where the total weight of the aircraft is considered to act. Its location has a direct impact on stability and controllability. As the center of gravity moves rearward, the aircraft becomes progressively less stable and more difficult to control. An aft center of gravity that exceeds limits can make it impossible to recover from a nose-high attitude. Conversely, a center of gravity too far forward increases the load on the tail and may prevent you from achieving the nose-up pitch needed for a proper landing flare. Always verify that your center of gravity falls within the approved envelope before every flight. The relationship between the center of gravity and the center of lift is fundamental to aircraft stability and control. In a normally loaded aircraft, the center of gravity sits forward of the center of lift. This creates a natural nose-down pitching tendency, which is a fixed force. The horizontal stabilizer and elevator then provide the variable nose-up force needed to maintain level flight, and that force changes with airspeed, giving the pilot the control authority needed throughout the flight envelope. When the center of gravity shifts too far aft, a critical problem emerges. The elevator may no longer be able to generate enough nose-down force to break a stall and recover. This is a potentially fatal condition, because a stall at the wrong moment with an aft center of gravity could become unrecoverable. On the opposite end, a center of gravity that is too far forward means the elevator cannot produce sufficient nose-up pitch authority to flare the aircraft during landing. The result is a hard, fast touchdown that can damage the aircraft or injure occupants. Always verify that your loaded center of gravity falls within the approved limits before flight. Both extremes carry serious consequences. Every airplane, regardless of size or purpose, is built around the same 5 major structural and functional components, and understanding each one is fundamental to your development as a pilot. The fuselage is the central body of the aircraft. It houses the crew, passengers, and cargo, and serves as the primary structural connection point for all other components. Attached to the fuselage are the wings, which are the main lifting surfaces of the aircraft. Wings can be positioned at the top, middle, or bottom of the fuselage, and most modern aircraft use a single wing or monoplane. Design. At the rear of the aircraft is the empennage, or tail group. This includes the fixed horizontal and vertical stabilizers, as well as the movable control surfaces, the rudder, elevator, and trim tabs, which allow the pilot to control the aircraft's direction and attitude. Supporting the aircraft on the ground is the landing gear, which can use wheels, floats, or skis depending on the operating environment. The two most common configurations are tricycle gear and conventional, or tailwheel, gear. Finally, the power plant consists of the engine and propeller. Beyond generating thrust, the power plant also supplies electrical power, a vacuum source for certain instruments, and heat for the cabin. Together, these five components form the complete aircraft system. The wing's internal structure is built around three essential components that work together as an integrated load-bearing framework. Understanding how each element contributes to the overall strength and shape of the wing is fundamental to understanding aircraft structural integrity. Spars are the primary structural members running spanwise along the wing. They are the main longitudinal beams responsible for carrying the bending and shear loads generated during flight. Most wings use either a single main spar or a combination of front and rear spars to handle these forces. Ribs run chordwise, forming the cross-sectional frames that give the wing its characteristic airfoil shape. They also play a critical role in transferring aerodynamic loads from the skin into the spars, ensuring forces are properly distributed throughout the structure. Stringers run longitudinally alongside the spars and work in conjunction with the wing skin. Their primary function is to stiffen the skin and help distribute aerodynamic stress across a wider area, preventing buckling and maintaining structural rigidity under load. Together, these three components, spars, ribs, and stringers, reinforced by the outer skin, create a structure capable of withstanding the significant and varied loads experienced during normal flight operations and beyond. The wing's control surfaces give the pilot precise authority over how the aircraft rolls and manages lift, and understanding how they work is essential for any aviator or aviation professional. Let's start with ailerons. These are positioned along the outer half of the wing, from the midpoint out to the wingtip. Ailerons work in opposition to each other. When one moves up, the other moves down simultaneously. This differential movement changes the lift produced on each wing, causing the aircraft to roll around its longitudinal axis. That's the axis that runs nose to tail through the center line of the aircraft. Flaps occupy the inner portion of the wing, from the fuselage out to the midpoint. Unlike ailerons, flaps are a temporary tool. They extend downward to increase the wing's camber, which is the curvature of the wing profile. This boosts lift at slower air speeds, which is exactly what you need during takeoff and landing when the aircraft isn't moving fast enough to generate sufficient lift on its own. Together, ailerons and flaps give the pilot control over two critical aspects of flight: lateral maneuverability and low-speed lift management, each surface designed specifically for its location on the wing and its role in flight. The empennage, sometimes called the tail group or tail assembly, is the collection of surfaces at the rear of the aircraft responsible for stability and control. Understanding how these components work together is essential for any pilot. The empennage consists of both fixed and movable surfaces. The fixed surfaces, the vertical and horizontal stabilizers, provide passive stability, helping the aircraft resist unwanted changes in its flight path. The movable surfaces give the pilot active control over the aircraft's attitude. The rudder is hinged to the vertical stabilizer and controls yaw, which is the rotation of the nose left or right. The elevator is hinged to the horizontal stabilizer and controls pitch, moving the nose up or down. Trim tabs are small adjustable surfaces mounted on the primary control surfaces. Their purpose is to reduce the sustained pressure a pilot must apply to the controls during extended flight, effectively allowing the pilot to trim off the load. Some aircraft replace the conventional horizontal stabilizer and elevator combination with a stabilator, a single one-piece surface that pivots as a whole unit. Because the stabilator is highly sensitive, it incorporates an anti-servo tab, which moves in the same direction as the stabilator to increase control feel and prevent over-control. Knowing these components and their functions will be critical as you study aircraft stability and flight controls. Landing gear serves as the aircraft's primary support structure whenever it's in contact with the ground, water, or snow, and the type of gear installed has a direct impact on how the aircraft handles in those environments. The most common configuration you'll encounter is tricycle gear, which places the nose wheel at the front and the two main wheels behind. This arrangement gives the pilot excellent forward visibility on the ground and provides inherent stability during taxi, takeoff, and landing, making it the preferred choice for most modern training and transport aircraft. Conventional gear, often called tailwheel or tail dragger, reverses that layout by positioning the main wheels forward and a small wheel at the tail. This configuration is lighter and more efficient in certain applications, but it requires greater pilot skill to manage on the ground due to its tendency toward ground looping. You'll find it commonly on older designs and aerobatic aircraft. For operations away from traditional runways, floats replace the wheels entirely to allow water takeoffs and landings, while skis are fitted for use on snow and ice surfaces. As you progress through your training, understanding these configurations will help you recognize how gear type influences aircraft selection, ground handling technique, and the environments in which a particular aircraft is certified to operate. The engine is the heart of the aircraft's power plant system, and it does much more than simply move the airplane forward. Yes, it turns the propeller to produce thrust, but it also generates electrical power for your avionics and systems, provides a vacuum source for certain flight instruments, and in single-engine aircraft, it's the source of cabin heat as well. The engine is enclosed within a cowling or nacelle, which serves two important purposes. It streamlines airflow around the engine to reduce drag, and it directs cooling air across the cylinders to manage operating temperatures. Now let's look at the propeller. Think of it as a rotating airfoil. Just like a wing generates lift by creating high pressure below and low pressure above, the propeller creates high pressure at the back face and low pressure at the front face, converting engine torque into forward thrust. Blade angle is carefully designed to maintain a consistent angle of attack along the entire length of the blade, since the tips move faster than the root. Pitch refers to the theoretical distance the propeller would travel forward in one complete revolution through a solid medium. Propellers are specifically matched to the aircraft and engine combination to maximize efficiency throughout the flight envelope. The aircraft is made up of several critical subcomponents, each performing a distinct and essential function. Let's walk through each one. The airframe is the foundational structure of the aircraft. It is engineered to withstand all aerodynamic forces encountered in flight, as well as the static loads imposed by fuel, crew, and payload weight. Every other system depends on the integrity of the airframe. The electrical system generates, regulates, and distributes power throughout the aircraft. It relies on AC generators, auxiliary power units, and external ground power sources to operate flight instruments, anti-icing systems, and cabin lighting, among other critical functions. Flight controls govern the aircraft's attitude and flight path. The three primary control surfaces are the elevators, which control pitch, the ailerons, which control roll, and the rudder, which controls yaw. These surfaces are operated either directly by the pilot or through the autopilot system. Finally, the brakes. Aircraft brakes use hydraulic caliper pads that squeeze against a rotating disc, or rotor. These discs are made from either steel or carbon material. One important point to understand is that brake life is measured in landings, not miles. This is because each landing requires the brakes to absorb an enormous amount of kinetic energy in a very short distance, which places exceptional thermal and mechanical stress on the components. There are three primary methods used to construct aircraft fuselages, and understanding each one helps you appreciate how structural design has evolved over time. The truss structure is the oldest approach. It uses welded longerons, the main longitudinal members, braced by vertical and horizontal struts to form a rigid framework. Stringers and bulkheads are added to give the fuselage its basic shape, but the truss itself does not naturally produce a streamlined form. Early aircraft covered this framework with fabric. Later designs used aluminum sheeting. Monocoque construction takes a completely different approach, relying almost entirely on the outer skin to carry structural loads. While this produces a very strong and clean aerodynamic shape, it has a significant weakness. Any deformation or damage to the skin directly compromises the structural integrity of the entire fuselage. That limitation led to the development of semi-monocoque construction, which is the industry standard used in virtually all modern aircraft. In this method, the skin still carries a substantial portion of the load, but an internal substructure, made up of bulkheads, formers, and stringers, shares the bending stress. This redundancy means the structure can tolerate localized damage without catastrophic failure, making it far more practical and airworthy for real-world operations. Composites have been part of aviation longer than many people realize. During World War II, fiberglass was already being used in the fuselages of B-29 bombers, primarily for insulation purposes. That early application laid the groundwork for what would become a revolution in aircraft construction. By 1965, the FAA had certified the first all-fiberglass aircraft, the Diamond HBV, and just 4 years later, the Windecker Eagle demonstrated that a 4-seat, single-engine aircraft could be built almost entirely from composite materials. Fast forward to 2005, and more than 35% of new aircraft incorporated composites in some form. So what are we actually working with? Fiberglass offers good tensile and compressive strength, handles impact well, and is cost-effective, but it carries a weight penalty compared to newer materials. Carbon fiber takes performance further. It is stronger, stiffer, and significantly lighter than fiberglass, and can reduce weight by up to 30% compared to equivalent aluminum structures. The trade-off is brittleness under impact loading, which has important implications for inspection and damage assessment. Binding everything together is the matrix, typically an epoxy resin. Epoxy outperforms polyester in both strength and high-temperature resistance, making it the preferred choice in most aerospace applications. Understanding these materials individually is essential before working with them in the field. Composites offer some compelling advantages that have made them increasingly dominant in modern aircraft design. First, when properly engineered, they deliver significant weight savings compared to traditional metals. Their ability to be molded into smooth, complex, curved surfaces also helps reduce aerodynamic drag. Composites don't corrode, which is a major reason Boeing was able to increase cabin pressure and humidity levels on the 787, improving passenger comfort. They also exhibit excellent fatigue resistance, making them ideal for high-cycle applications like helicopter rotor blades. And in military aviation, their ability to mask radar signatures is critical. The B-2 and F-22 are prime examples. However, composites come with some important disadvantages that maintenance personnel must understand. A low-energy impact, something as simple as a tool drop, can cause internal delaminations with absolutely no visible surface damage. This is a serious inspection challenge. Heat is also a concern, as many epoxy resins begin to weaken above 150 degrees Fahrenheit, which is why white paint is recommended to reflect solar heat. Chemical paint strippers will destroy composite structures, so only mechanical removal methods are permitted. Finally, water can infiltrate honeycomb sandwich structures and cause significant hidden damage over time. Knowing these limitations is essential for anyone working on or around composite airframe components. When it comes to lightning strike protection, composites present a unique challenge that aluminum structures simply don't have. Aluminum conducts electricity naturally, so when lightning strikes, the energy spreads across the airframe and dissipates relatively easily. Composite materials, however, are poor conductors, which means engineers must add conductivity by bonding fine metal mesh directly into the skin surface. On fiberglass structures, aluminum mesh is typically used, while carbon fiber structures require copper mesh due to compatibility considerations. This is not just a manufacturing detail, it directly affects how you perform repairs. Anytime you restore a composite skin, that mesh must be properly reinstated to maintain the aircraft's lightning protection integrity. Skipping that step is not an option. It's also worth noting that fiberglass is transparent to radio frequency signals, which is why internal antennas work well in fiberglass airframes. Carbon fiber, on the other hand, acts as a shield and blocks those signals entirely, requiring external antenna placement. Looking at the broader picture, from light aircraft like the Cirrus SR-20 to large transport category aircraft like the Boeing 787, composites continue to expand their role in aviation. Their combination of design flexibility, corrosion resistance, and outstanding strength-to-weight ratio means this technology is only going to become more prevalent in the aircraft you work on throughout your career. Over the decades, cockpit instrumentation has evolved significantly, moving from traditional analog gauges to modern glass cockpit displays. In early aircraft, pilots relied on individual round gauges, each dedicated to a specific parameter like attitude, airspeed, altitude, or engine performance. While these instruments were reliable and well understood, the sheer number of them created cluttered panels that demanded significant mental workload to scan and interpret. Modern aircraft now use electronic flight displays, or EFDs, which replace those individual analog gauges with large LCD screens. One major advantage of these solid-state instruments is their dramatically lower failure rate compared to the mechanical gyroscopes and moving parts found in traditional gauges. In a glass cockpit, you'll typically find two primary displays. Directly in front of the pilot is the primary flight display, or PFD, which consolidates the most critical flight information, attitude, airspeed, altitude, and navigation, into a single integrated screen. In the center of the panel sits the multi-function display, or MFD, which can show moving maps, weather, traffic, engine data, and much more. Together, these displays give pilots a cleaner, more intuitive picture of the aircraft's state, reducing workload and improving situational awareness. When flying by reference to instruments, understanding how to categorize and use each instrument is fundamental to maintaining situational awareness and aircraft control. Instruments are divided into three functional categories: performance, control, and navigation. Performance instruments tell you what the aircraft is actually doing. The altimeter, airspeed indicator, vertical speed indicator, heading indicator, angle of attack indicator, and slip skid indicator all fall into this group. These instruments reflect the outcome of your control inputs. Control instruments, by contrast, show you immediate changes in attitude and power. The attitude indicator is the primary control instrument, and it allows you to make precise adjustments without directly referencing speed or altitude. Think of it as the instrument that bridges your input and the aircraft's response. Navigation instruments tell you where you are in relation to a fix or facility. This category includes GPU, VOR, NDB, and ILS indicators, which may present position information in either 2 or 3 dimensions, drawing from both ground-based and space-based sources. Understanding which category each instrument belongs to helps you scan the cockpit more efficiently and interpret information more accurately, especially during demanding phases of flight. GPS, or Global Positioning System, is a satellite-based navigation system originally developed by the U.S. Department of Defense for military use. It was made available for civilian use in the 1980s and has since become one of the most widely used navigation tools in aviation. One of its key advantages is reliability. GPS operates in all weather conditions, anywhere in the world, 24 hours a day. Understanding how GPS determines your position is important. With signals from at least 3 satellites, the system can calculate a 2-dimensional position, your latitude and longitude. Add a 4th satellite, and the system can determine a 3-dimensional position, adding altitude to the picture. Having additional satellites beyond that minimum improves accuracy by helping offset signal loss or ambiguity in the data. As a pilot, you'll rely on GPS extensively, so it's worth building a solid foundation in how it works and its limitations. This topic is covered in much greater depth in Chapter 16 on navigation, and you should also reference the Aeronautical Information Manual, or AIM, for authoritative guidance on GPS use in aviation. Keep those resources handy as you continue your studies. As we wrap up Chapter 3, let's take a moment to consolidate the key concepts you've covered. First, you learned how the FAA defines and certifies aircraft. Remember that standard airworthiness certificates are white, and special airworthiness certificates are pink, a detail that frequently appears on knowledge tests. Second, the 4 forces of flight, thrust, drag, lift, and weight, must remain in balance, and center of gravity position plays a critical role in maintaining safe, stable flight. Third, you examined the major components of an aircraft and how each one contributes to both structure and control. Fourth, aircraft construction has evolved significantly, from simple truss frameworks to advanced composite materials, which offer real performance benefits but demand specialized inspection and repair knowledge. Finally, modern electronic flight displays have transformed the cockpit environment. Understanding how performance, control, and navigation instruments work together, including GPS, is essential for today's pilot. These aren't isolated facts. They build a foundation for everything that follows in your training. Make sure you're comfortable with each of these areas before moving on, as they will appear throughout your ground school curriculum and on your FAA written examination.